Yeah, that's done. So, good evening, everyone. My name is Anay, and I'm a PMRF candidate pursuing my PhD at IISc Bangalore. And I'll be conducting these live sessions once every week, Tuesday, 7 to 8 p.m. The idea here is that every week we'll together try to solve some tutorial problems which will help elucidate the concepts which are taught in a week. So, like previous week was the week one. So, based on the topics covered there, we have selected a set of 10 problems which we'll be going through together. Uh, so, yeah, Rakesh, can you mute your microphone? Yeah, okay, thank you. I'm audible, right, everyone? Uh, cool. So now I'll be shifting to the presentation, and it's since it's full screen, I'll not be able to see the chat box popping up. So I would request you, in case you have any doubts or during any interaction, to kindly unmute yourselves and yeah, and participate in it. So let me know when my screen is visible. Okay. Is the screen visible? Okay, cool. Again, unmute yourself when answering, okay? Because once the presentation starts, it may not be possible for me to look at the chat box. So, okay. So, is the presentation visible as well?
Yes, sir.
Okay, cool. Thank you. So all of you have taken the course Solid Mechanics. It is being offered by Professor Ajit Kumar from IIT Delhi, and the course code is NOC 22 ME70. This is the tutorial for the first week. So in the first week, uh, you must have learned the concepts of like representation of a vector, mathematical operations such as dot and cross product, what's like a scalar vector, a second order tensor, then the rotation matrix. You might also have learned some concepts about traction and how we can calculate the traction at any arbitrary plane, provided that we have the traction values on three independent planes. And finally, you must have touched upon the concept of stress tensor and how to go about calculating it and what it physically represents. So, okay, so let's start with a simple problem. So, uh, the first problem asks which of the following statements are true. So more than one of these can be true. So let's go through them together. The first statement is scalars are zeroth order tensors. So can anyone tell if this is true or false?
True.
True, correct. Uh, do you have any particular reason?
Actually, scalars are of rank 0. For
Hmm.
vectors, rank will be 1, and rank will be 2 for tensors, I think.
So yeah, scalars by rank zero. Scalars essentially only have a magnitude, like energy. So it or pressure, it only has or temperature, it only has like one value associated with it. So the first statement is true. Scalars are zeroth order tensors. Are tensors independent of coordinate system?
Yes,
Correct. So, as an example, I'll take a vector. The annotations are visible, is it? Or
Yes, sir, visible.
visible, right? So, suppose I take this particular vector in a particular frame E1 and E2. This is my vector V. I can say change the frame of reference to something else, like E1 hat and E2 hat. What this essentially would do is change the representation of vector V from coordinate system E1, E2 to a different to a different representation vector V in coordinate system E1 hat, E2 hat. This representation may be different, but the vector itself is unchanged. So, as someone correctly pointed out, it is true. Uh, Third, are vectors more general than tensors?
False.
Correct. So scalar is zeroth order, tensor vector is the first order. Then, as you must have seen, stress is like a second order tensor. And fourth, one can add tensors of different orders.
No.
Again, this is obviously false because, as an example, you can have like a say scalar which is a zeroth order plus a vector which will have like three components v1, v2, v3. You cannot add these three. Add this cannot be done. So yeah, so the first two are true, the next two are false. I think someone is joining. Is it? Okay, no. Uh, Good. So, second problem. What is the product of a scalar with a vector? So, you have a scalar S and you have a vector V, which, if represented in, say, E1, E2, and E3 coordinate frame, will have certain components V1, V2, and V3. So, what is the product S into V?
It's a vector.
Correct. So we simply multiply the scalar S with each of the components of vector V, which are like V1, V2, and V3. And so the end product is simply S into V1 to S into V3, which is a vector. Okay. So the third problem. What can we say about the rotation tensor? So if you guys remember, rotation tensor, I'll denote it by R.
It should be orthogonal.
Yes, correct. Rotation tensor R essentially takes rotation tensor R will essentially map a base an orthonormal basis E1, E2, E3 to another orthonormal basis E1 hat, E2 hat, and E3 hat. It's a second. It's a As someone pointed out, all the sorry you it's all its columns are essentially orthogonal to each other. And by the definition, it actually, as I mentioned, it uniquely relates a set of three orthonormal vectors to another set of three orthonormal vectors. Is the determinant of this rotation tensor in its matrix form? So rotation tensor in matrix form, is this determinant equal to 1 or minus 1? Does anyone remember? Okay, so the determinant of the rotation tensor in its matrix form is equal to 1. This is equal to plus 1. So this is from the definition, so the third statement is wrong. And fourth, as I mentioned, it's a second order tensor. So okay, then which of the following, the fourth question asks, which of the following holds true about traction? So if you guys remember,
It's a vector quantity.
correct. So traction is defined using two parameters. First is the position x, second is the normal, second is a plane whose normal is given by n. So you have t x comma n. This is how it's denoted. So yes, traction is a vector quantity. It's essentially limiting limit of the force vector upon the area around the point x. So like this area, this small area delta I, it's a vector quantity. Also, is it constant throughout the body or can it vary from point to point?
It varies from point to point and also depends on the direction.
Yes, exactly. If we take like a different plane here, let's say n dash, you'll have a different traction corresponding to it given by t cap. Uh, Traction, as we mentioned, it varies from point to point. It can vary from point to point, and at any given point, it doesn't have a unique value because t not only depends on the point x, but it also depends on the plane, uh, plane on which we are looking, plane on which we are probing for the traction. So n can change, therefore t also can change. So third one is wrong, and obviously since it's a vector, this is also wrong. Okay, so the fifth problem asks if there is a relation between traction at a point on planes which are which have like opposite directed normals. So we are looking at a
Negative of each other.
correct. And can you tell quickly why?
Maybe action reaction. Newton third law.
Exactly, correct. It's precisely due to that only. So yeah, that was quick. They are they are negative of each other. So at a point x, if we are looking for traction on say plane n, this is related to traction on the same point but with a plane which has oppositely directed normal. So okay, what can you say about the stress tensor? So is the stress is the so stress tensor is this, right? So if we want to write it in a matrix form, if we want to represent it in, sorry, coordinate system e1 e2 e3, so is this representation a matrix for the stress tensor? Is it a 3 by 3 matrix, or is it a 2 by 2 matrix, or is it a vector, or is it a scalar?
It's a tensor. It's a 3 by 3 matrix.
3 by 3 matrix.
Tensor
So
of rank 2.
correct. So it this automatically rules out the last option, which is saying that it's a vector. Then, if you guys remember how we write the in matrix notation, I've seen. So this comes from the, like if you have three lanes, so you just do ti first. Sorry. we do a tensor product between tractions on three different planes. uh, okay, so this is the matrix form, a 3 by 3 matrix. So are the components on the diagonal, these, are they, do they signal normal component of the traction?
Yes.
Yes, exactly. And what do the off diagonal terms, uh, what are they physically?
Shear components of traction.
Correct. So we can also write this as, so these sigmas are your sigmas, sigma xx, sigma yy, sigma zz. These are your normal components, and tau xy, tau xz, tau yz. These are your shear components. Okay, so that was also okay. So the stress sensor at a point in the body is unique, although there are infinite tractions associated with different planes at a point. So is this true or false?
True.
Correct. So I think this diagram is in the video lectures. So you have like a force P, you're looking at the location X, and you can calculate, say, the traction at this plane, and that traction would be something like T by E1. Right? But if you calculate the traction on this plane, say, n hat, then your T hat would actually, if this angle is cos, is this angle is theta, then T hat would actually come out to be P upon A by cos theta, which is the projected area. Right? So traction can change. So, okay, what can you say about the stress matrix at a point in the body? So they are using the word matrix, so it means not this, it actually means this. So this is what they are asking about. So are so first question I would like to ask is like, is this always the same regardless of, say, the coordinate system that you have?
Stress matrix may vary depending on the coordinate system.
Correct. So if you go back again to the definition of how you calculate, you would have something like this tensor product, summation of this tensor product gives you stress matrix representation of the stress tensor. So if these vary, you may end up with different values here. So the tensor in itself is same, but the matrix representation is can change. This is similar to how, like, the representation of a vector in terms of its components can vary based on what coordinate system you are using. So stress matrix is not unique. It's will be different for different coordinate system. So, yeah. So the ninth problem. So suppose the traction vector on planes perpendicular to axis E1 and E2 are known. Let us draw that. So this is your body. This is your point X. This is E1. This is E2. And the one coming out of the plane is E3. So what they are giving is T at X with a plane which is normal to vector E1. Suppose this is given the way T1. Similarly, T at X normal at E2 is given T2. Correct? So these two values are given, and then we are asked what sort of tractions can we obtain using these two values. So okay, does anyone okay, you guys remember this formula for traction? Summation Ti Ti times Ei dot n. So if you want to calculate traction at a point x in a given plane n, for a plane whose normal is given by n, then you simply need to cal simply need to sum simply need to find the sum. So T1i into E1i dot n. Okay. Now we know T1, we know the values of T1 and T2. We are asked for what sort of n can we calculate these values. So we first know that E1 is perpendicular to E2, which is also perpendicular to E3, and these two are also perpendicular to each other. So all these three are normal to each other. And we also know that, suppose let's say you have n lying in the even E2 plane, which is the first option, right? So we can write n as a linear combination of vectors E1 and E2. So Le1 plus Me2. Therefore, if you do n dot E3, what you'll get is L1 E1 dot E3 plus M E2 dot E3. But since these are orthonormal to each other, E1 dot E3 will go to 0 and E2 dot E3 will also go to 0. Therefore, n dot E3 will be equal to 0. Now, if we want to calculate, sorry, I'll label this as n star. So, n star is like we are talking about this option, first option. N star is a vector which lies in the E1 E2 plane, and n star essentially denotes a particular norm. So if you want to calculate T star of x comma n star, then we'll have T1 E1 dot n star
Sir,
plus,
his answer is 1.
yeah, I was just deriving that. So n star E3 dot n star. As we saw, this goes to 0. So even if we don't know T3, we don't need to worry about this. We can calculate these two provided we know L and M, and therefore we can calculate T for corresponding to plane normal n star which lies in the E1 E2 plane. So the answer is the first one. This is clear, right? It's not. Is anyone finding this difficult, or are you able to follow so far? Okay, so I'm assuming that your silence means that you are comfortable so far. If not, please raise your voice now. And yeah, so the final problem is a true or false. So the normal component of traction on E1 plane, so which is normal component of traction on E1 plane equals the shear component of traction on E2 plane. So what they are saying is, if we have T1 and if we have T2, as T1 and T2 as the tractions for E1 and E2, is the normal component of T1, which is T1 dot E1, Is this equal to the shear component? Is this equal to T2 dot E1? So is this will this be true in general? If I say write down T1 as its vector component, so you'll have T11, T12, T13. If I write T2 as T21, T22, T23. So what this question is essentially asking is normal component of traction on E1 plane, which is T11, is this equal to shear component of traction on E2? So like is it equal to T21? Are these true in general? Is the statement true or false? Okay, so
False.
yeah, in general it will be false. So there's no, uh, it's not necessarily true. There's no mathematical relation forcing them to be true. So these were some of the problems that I've chosen for this particular tutorial. So if you guys have any particular doubts based on the video lectures, you can ask them now, or you could always also post them on discussion forum. So we look out for it. I think someone recently posted 1 or 2 days, I think couple of days ago. So do make use of that. We are here to essentially help you learn this subject better. Do you have any doubts so far? How are you finding the course? Like, are you guys able to follow?
Yes, sir, but little bit tough.
Little bit tough. Okay. Can you tell like what particular parts you are struggling with so that I can try to better address those?
Actually, in derivations like linear momentum balance, angular momentum balance, actually, in derivations, we are finding somewhat tough.
So, were you, for example, there is this derivation for finding the traction on any particular plane that makes use of uh, conservation of linear momentum, right? So, were you able to understand that, or do you want me to go through that now?
Oh, no need, sir, no need.
Okay, so one of the things I want to say is that these sessions were essentially created in an attempt to help bridge the gap. Like, say, sometimes we see a video lecture and we think, okay, we are understanding it, but then we go back and we think, okay, I'm probably not able to understand this, or this particular thing seems unclear. So, what we are trying to do on our end is come up with a few problems which would elucidate, which would help understand those concepts better. That is how like these particular problems were chosen. So, if you apart from this, if you have any doubts, do let me know now so that I can try to include something in the next week's live session. And again, use the discussion forum whenever necessary. It's like we are all friends here. We all want to learn. So yeah, like while teaching you guys also, I'm also able to learn a few things. So okay. Yeah, if anyone doesn't have any doubts, then yeah. Thank you so much for attending today's live session. We'll have the next one for based on week two's contents in the coming week on Tuesday, which is 9th of August, same time, 7 p.m. to 8 p.m. Thank you.
Thank you.